Hey guys, this is like a fun one. So we've got the integral of the maximum of x, x squared and x cubed, all between -2 and 2. So to solve this, we need to figure out which function is biggest and when, i.e. over what interval of x is each one the maximum. So the first thing we can spot, we have x and x cubed. Both of them have odd powers. So if we input a negative into that, we're going to end up with a negative coming back out the other side. But for x squared, that's an even power. So if we put in a negative, we receive a positive on the other side. So that tells us then, whenever we have x being negative, that we can think about what the functions are going to give us. X will be negative, x squared will be positive, and x cubed will be negative. So on this interval, we have to use x squared. So what I'm going to do down here is make a little list. So x being negative, we have to use x squared. Next then, whenever we have a positive x, we need to kind of compare all the functions and see which one's the biggest. So let's start with the two biggest powers and think, when is x cubed bigger than x squared? So to do this, we're going to take away x squared from both sides. That's going to give us x cubed minus x squared is going to be positive. And now if we factorise an x squared out, we'll have x squared on the outside, x minus 1 inside the bracket, and that again, all being positive. This is a cubic, and it's going to have critical values, which are basically like the roots of it, of 0 and 1. But notice we had the x squared here, so that 0 is a repeated root. So what that's going to tell us is that's like the turning point of a cubic. So if we do a very quick sketch of it, we end up in this sort of scenario, where this is going to act like a repeated root. So the actual x-axis runs along that line with the coordinates of 0 and then 1 being on that side. So the question is, when is this positive? Whenever we're bigger than 1. So for this then, we end up with a situation where x needs to be bigger than 1. So now then, when is x cubed bigger than x? Similar sort of process. Let's subtract the x on both sides. So x cubed, take away x being positive. We'll factorise an x out, and we'll have x squared minus 1 inside the bracket. And this then is a difference of two squares. So we can expand that out into two separate brackets, with one of them being x plus 1 and one being x minus 1. And we still have that x on the outside as well. So this has critical values, again of the 0, but also of a minus 1 and a positive 1. All three distinct roots. So when we go to sketch the cubic, something like this, three distinct roots, minus 1, 0 and 1. We want it to be positive. So we've got two different regions, in between the minus 1 and the 0. And then whenever x is bigger than 1. Of these two intervals, this one is purely negative. And we know already that x squared wins in that region, so we don't need to really worry about that at all. So we just are concerned about the x being bigger than 1 for that region. And what we can see now, for both cases when we're thinking about x cubed being bigger than the other two functions, that happens whenever x is bigger than 1. So over this interval, x cubed is always the biggest. So that's another one we can put down here. X being bigger than 1 tells us we have to use x cubed. So now then, we just need between 0 and 1, see which one's going to be the biggest then. We compared x cubed with both functions, but we haven't compared these two functions with each other. So let's see, when is x squared going to be bigger than x? Again, similar sort of process. Subtract x on both sides. We end up with a situation where we can factorise that now. Bring an x on the outside, x minus 1 on the inside. This is a quadratic with critical values, so again, sort of like the roots, of 0 and 1. So if we sketch that quick, something like this, 0 that side, 1 over there. So what we can see, we're looking for when this is positive. This happens outside of 0 and 1, but the region we're interested in is 0 to 1. So we actually want when this is negative. So we want the opposite of this, which means we want the opposite of this and the opposite of this. So that tells us x is bigger than x squared between 0 and 1. And actually, if we look at above, the bit we did with x cubed and x, we get that same region of 0 to 1. But again, we want the opposite. So the opposite of this, and of this, and of this, and therefore the opposite of this. So what that tells us, in the region 0 to 1, x is always the biggest. So that wins in that region. So now then, we've covered our entire range from -2 to 2. We didn't think about the equal parts, but actually they're all equal at 0 and 1. So it's not too much of a worry to really have to think about. Because no matter which function we put there, we'll always end up being the biggest one kind of by default. So now then, we need to do our integral, if we just label that I. We can actually compute it is going to be the integral from -2 to 0 of the winner in that region, which was x squared, plus the integral from 0 to 1, the winner in that region was x. And then the last region, 1 to 2, the winner was the x cubed. So computing all of those, x squared, we raise the power to cubed, divide by a 3, and we need to sub in the limits of 0 and -2. For the x, becomes x squared over 2, with limits of 1 and 0, and the cube is going to go up to a 4, have a 4 underneath, and the limits here are 2 and 1. So when we start subbing the numbers in, 0 here and the 0 here, both of them inside are polynomials. So whenever we stick the 0 in there, we're just going to get 0 back out. So we can kind of ignore them straight away. So now we need to take away the -2 subbed into this. -2 cubed is -8. Divided by 3 is just -8 thirds. Combined with this negative, it's going to make it positive 8 thirds. Sub a 1 into here. 1 squared is 1. Over 2 is a half. And for the x to the 4 in the end, subbing in the 2. 2 to the power of 4 is 16. Over 4 is going to give us a 4. So add in that one. And then taking away subbing in a 1 there. 1 to the power of 4 is 1. Over 4 gives us a quarter. Looking at the fractions here, we have 3, 2, and 4 in the bottom. So we can have a common denominator of 12, i.e. the lowest common multiple of 2, 3, and 4. So for each fraction, what number do we need on the top now? For the 8 thirds, times top and bottom by 4, we get 32. For the half, top and bottom needs to be times by 6, so we're going to get 6 in there. For that 4 by itself, there's no denominator at the minute, so it has to be a 12 down there. So again, times by 12 on the top, gives us 48. And then the quarter we have in the end, top and bottom by 3, so we get a 3 on the end. Last step then, adding all these numbers up. 32 and a 6 is 38. Add a 4 is 78. Add the 8 is 86. Take a 3 is 83. So our final answer will be 83 over 12. Lovely jubbly.